Greetings, students, and welcome to another video lecture about a discrete probability distribution. This one is a common one, so it gets its own shout out. It is the binomial probability distribution that we're going to talk about. So let's begin. So what is a binomial probability distribution? So we're going to start with an example here to get us thinking about this. So suppose we're taking a multiple choice quiz and we're just going to guess, completely guess at answers. So in order to figure out the probability for the random variables, let's be very careful and clear when we define the variable. So let's suppose that X represents the number of questions you got right. So since it's multiple choice, there's one right answer. If there are 4 possible answers, then there are 3 wrong answers. So if we got none of the question right, so we got 3 wrong answers to choose from, then in order to get 0 right for this quiz, we would have a 3 out of 4. And since the only other option is getting 1 question right on a 1-question test, we already said that that was 1 out of the 4 options. So here we have a probability distribution for a discrete random variable X. And this should be pretty straightforward. So if you have 4 possible answers, there are 3 wrong and there's 1 right. Now the matter gets a little bit more complicated if we introduce another question. So now we have 2 questions instead of 1. And still X represents the number of questions you got right. Since it's a 2-question quiz, you could have 0 right, you could have 1 right, or you could have 2 questions right. So now the probability comes from the probability rules that we've discussed before. So if you have 2 events that happen together, so let's say for the top one, I get the first question wrong, and then I get the second question wrong. There's an and for those events, so there's going to be a multiplication. So the multiplication rule comes into play, and the probability of getting 1 wrong, and then the probability of getting another 1 wrong would be 3/4 times 3/4. So let's talk about that. So if we take 3/4 over 3/4, we get 9 over 16. And we can also turn that into a decimal. And the decimal is between 0 and 1, so it's a probability. And like I said, we had the situation where we got both wrong. Now, the bottom one was really easy. What would the situation be if we got both right? Well, that would be a 1 out of 4, 1 out of 4, so 1 out of 16. So right here, we got them both right. Here, we got them both wrong. And then, of course, the middle is we got 1 right and we got 1 wrong. But this violates the rules of a probability distribution. Do you see why? So the problem here is this last line, the total, is supposed to sum to 1 if all of the probabilities are here. So clearly we're missing something in this thought process. Pause the video here and see if you can think what it is. All right, welcome back. So were you able to figure out what was wrong with our reasoning? Well, let's look at this middle line. So this middle line and this total don't align. We don't have 1. And the top one, the only way to get 0 questions right is if you get both wrong. And the bottom one, the only way to get them all right is to get them all right. But this middle one, there's 2 possibilities. We could get the first question right and the second one wrong. Or we could get the first one wrong and the second one right. So there's 2 ways to get 1 question right. So let's see if that fixes things. So let's focus back on this line and let's put a 2 here because there are 2 ways to do it, as we just saw. And if we multiply that value by 2, it doubles it. And lo and behold, we get our value 1 that we were looking for. So herein we've fixed our mistake. Okay, but this is going to get more complicated as we go. Let's try this example. Now, each example, we're only increasing by one question, but each time we add one question, things get a lot more complicated. So there's got to be a better way to do this. If you want, you could try doing this by hand and see what you get. But we have this idea of the probability of getting something right and the probability of something wrong. There are only two possibilities, right? It's right or it's wrong. And using that information, we can create a binomial probability distribution. So it's a binomial distribution if the following is true. The number of experiments performed, we're going to call them trials, are discrete. The trials are independent, so one does not impact the results of the next. For each trial, there are two mutually exclusive outcomes. So this is the idea of success or failure. Can you clearly define it as an either or situation? And that's why it's called a binomial. There's two possibilities, two and only two. And the probability of success and its inverse failure are both the same for each trial. So each time I look at a question, the chance of getting the question right or wrong is the same. So you can't change type of question partway through for this to work. So the notation for a binomial distribution, probability distribution, we're going to use n to represent the independent trials of the experiment. So basically, how many times are we going to do whatever it is? In this case, we were talking about test questions. So n would be the number of test questions, as this example goes. Let P denote the probability of success for each trial. And therefore, 1 minus P is a probability of failure, because since there are only two options, there's either the probability or its complement. So that's why we have P and 1 minus P. In the case of the example we just did, we know 1 out of 4 questions, out of 4 multiple choice answers is correct. So the probability of success for a multiple choice test is 1 over the number of choices. So in this case, it would be 1 over 4 is the probability of success. So P would equal 0.25. And therefore, 1 minus P is 0.75, which is 3 out of 4 are the wrong answers. And last but not least, we define X as a number of successes in the independent trials of the experiment. So X has to fall between 0 and n and include 0 and n. Now I know that's a lot. Let's put it into an example and see what it looks like. For real world examples, you could look at sexually transmitted infections. You either have it or you don't. So here you could use this pie chart to determine probability of success. Also define success very clearly. Is success not getting the infection? So sometimes success may sound like you don't want it. So be very careful when you set the problem up that you're clear about what the term success means. So I just threw that in there as a real world example. But let's look at the notation. So the notation's a little scary, and this is why Excel is a wonderful thing, because it will take care of calculating the binomial probability distribution for any value of X for you. But just to let you know what it looks like, up at the top, it says that the probability of X, so that X is the number of successes we want. As you remember in the table above, it cycled from 0 to 3 for the last one. You'll have that equal to the number of ways to choose those items in that way. So remember when we talked about 2 questions, there were 2 possibilities that you could either have the first one right and the second one wrong, or the second one right and the first one wrong. And with those variations, that would be where the 2 came in. So remember that 2 in the front, that would be where that NCX is. And that's known as a combination. It's a number of ways things can get reordered. Again, Excel does that calculation for you as well, so we didn't dive too deep into it. That's also what we use to figure out the probability of winning the lottery. So if you're interested in that, we could have a side conversation about the lottery since it's getting so big for this Friday. Now the probability P there, again, is 0.25 in the example that we were talking about, and then the number of successes you want for that row. And then the probability of failure and the number of failures in that row. So this sounds like a lot, but again, Microsoft Excel can do it. Here I've put what the formula is for Microsoft Excel. You could also use a TI-84, but we're not using that in this class. So the Excel formula is right there for you. It's the equal binom.dist, and that stands for binomial distribution. Statisticians are not creative, so that's why it's named like that. And you put X, which is the first column in your probability distribution. N is the total number that you could go up to. P is probability of success. The reason it says false in that formula is because you do not want it to be a cumulative frequency. You want it to be at one value. So you put false. Otherwise, it'll want to create a cumulative probability, which is not what we need in this case. The other benefit of having a binomial distribution, aside from being able to calculate it using Excel, is that down here, the expected value, we don't have to do that table calculation that we did before, because the binomial distribution has this very special relationship for expected value, where it's simply the total number of independent trials or experiments times the probability of success. So you multiply those two values and you have your answer. For the standard deviation, it's also pretty straightforward. You take the square root and you multiply the probability of success times the number of independent trials times the probability of failure, which is why we have 1 minus P. All right, so let's put it into practice. So here I went all out. And instead of doing just a few questions, I've gone up to 5 questions on the multiple choice test. This I would not want to do by hand, but it becomes a lot easier to do with Excel. Now, as I said, you have the formula there that looks really complicated. I put it there to show you what it looks like and how the values change. But the important thing you need to note is at the bottom, it tells you how to figure out these values in Excel. And you could try that out. So you could input for the first row equal binom.dist for 0, 5, 0.25, false, and see if you get 0.2373. So pause the video right here, go try that out, and come back when you're done. Okay, great job. I hope that worked out. If you want more practice, you could try the other values as well. And we're going to continue on now. So as I said before, for random variables, we did a lot of work to calculate expected value by multiplying the data point, the random variable in this case is X, times its probability, and then adding all of those up. The standard deviation is a very complex calculation. The formula is right there. We walked through it in the last video. You can refer to that again if you want to. But here we're just going to jump to the punchline. And what we're doing is we're showing that those shortcuts for the binomial distribution work. So this is the long way of calculating the expected value for the random variable. As you can see, doing this long way of multiplying the random variable by its probability and then summing up all of those values to give us 1.25 gives us the exact same value as if we just multiply n times p, where n in this case is 5, p is still 0.25, and you get the exact same value. So you can see I'm not lying. There is this shortcut. It's something we love. Make sure you write this formula down someplace for easy access. So when you see binomial distribution, you can just pull this out. We can also prove that the standard deviation formula works. So the top one here is the long version, and down here we create a table of values To do all of that complex calculation, we add up this entire last column here, put that value under a square root and get 0.97. If we do the shortcut formula where we multiply n, in this case 5, by the probability of success of 0.25 times the probability of failure at 0.75, we will also get 0.97 in the long run. So clearly these formulas work because they match the output from the long table calculation for the binomial distribution. And note, this is only for the binomial distribution, not for any random variable. This is a very special random variable. Now we're looking at a new problem on smokers. So let's say that in a survey, we find that 90% of adult smokers start before 21. So we're going to survey 10 smokers, 21 years or older, randomly, and figure out the number of smokers who did start before 21. So the most important thing is to notice that it's a binomial experiment and explain why. So in this case, all the events are independent. We're assuming the people are not influencing each other because they were randomly selected. The variable is quantitative and discrete. So we are counting people. So it has to be a discrete value. And the probability is an either or situation. So in this case, individuals either started smoking before 21 or after. Those are the only two possibilities here. And we have various probabilities listed here. Notice how we're missing one at 8. So the random variable at 8 is not calculated yet because we're going to do it right now. So if we are trying to find the probability that exactly 8 people started smoking before 21 years of age out of our sample of 10, we can use this formula here that's really complicated and crunch through the values, or we use Excel. And Excel allows us to do it a lot quicker. We'll use equal binom.dist. We want 8 because x is 8. We want 10 because there are 10 total values. If you look at the last number in the table, you'll figure out what the big total is. 10 smokers is who we surveyed, so that's everyone as well. So that's where the 10 comes from. And this 90% of adult smokers is why we have 0.9. And last but not least, false is because we do not want to add up all of the probabilities up to 8. We want just 8. Now, I keep saying this word cumulative. We don't want to add it up. Well, in this case, we do. Suppose that we're looking for the probability that fewer than 8 started smoking before 21. Now, this is where we have that practice in the other probability video where we talked about no greater than and these confusing ways that things are phrased sometimes. So here, fewer than 8 means less and not including 8. So we wanted to add up 0, 1, 2, 3, 4, 5, 6, 7. All of those probabilities to figure out what fewer than 8 is. So now down here, if probability of x is less than 8, that is the same as the probability of x less than or equal to 7 for discrete. Only for discrete do we need to worry about that. So here I magically have a value, but I got it by using the binomial distribution again in Excel. So this is equal binom.dist, open parenthesis, 7, because that's the biggest number I want to add up to in terms of these probabilities. There's 10 total, so they know how big the sample is. And there's 0.9 from the 90% of adult smokers. And this time I put true. And again, the reason I put true is I want to add up to 7. So this says take every value, add it up until you get to 7, include that one, and you're done. So it will stop after it adds that value at 7. Now, suppose I want 8, 9, and 10. So this is the probability that at least 8 So at least means 8 is the least. So we want 8, 9, and 10. And I stop at 10 because we don't have more than 10 smokers, so we can't go past 10. So you might remember from the probability video, the complement rule. Now the complement rule states that if you're looking for one probability, you could find that by finding its complement and subtracting it from 1. So if the probability of x greater than or equal to 8 plus the probability of x less than 8 would equal 1, you can actually subtract one from the other in order to get the value that you're looking for. Now, why did I do this? It's because in this last slide, we already found p of x less than 8. And we found it was 0.0702. So we can go back and we already did that. So since we have information already, we might as well use it. So if you are trying to get values greater than a certain value, you actually have to take 1 and subtract off the values below. And the reason for this is because, as you can see in this previous slide, this binom.dist command only has this format. So it will always start at the value of 0 for x and work its way up to the value you list in this first spot. So computers are not the brightest. They can only do certain things. So in this case, it can only add from 0 up to the value you specify. So if I want to go from 8 and higher, I have to actually take off all the other probability instead. So I'll do 1 minus the probability of x less than 8. Or in this case, x less than or equal to 7, in order to create the formula for Excel. Which really complicates matters when you do something like this. If we're interested in the probability of the number of smokers being between 7 and 9 inclusive, which means also including 7 and also including 9, how do we do that when I just said that the binomial distribution formula in Excel starts at 0 and always works its way up? Well, the solution to that problem lies below. What we can do is we can add all the way up to the value that we're interested in this case, 9. So we're going to take from 0 to 9 and add that together, and then we'll subtract off the part we didn't use, which is 0 to 6. So here we have the probability of x less than or equal to 9, the probability of x less than or equal to 6, and we're going to get the probability of x less than or equal to 9 by this first formula. And x less than or equal to 6, that probability comes from this binomial distribution formula right here. And that is it for binomial distribution. Excel has the 2 commands. Well, actually, it's just one command, and you either put true or false. False means it's an exact value of x or the random variable. True means you add from 0 up to that number that you're interested in your probability question. So I hope this was informative and that the other material is clear. That's it for discrete random variables. I will see you in the next video where we dive into continuous.